Lesson 3, the contrapositive, the converse and inverse, and IFF statements. Okay, so it's all about definitions today. It's all about just knowing if they want the contrapositive, how do you get the contrapositive? The converse, the inverse, how do they relate? Okay, so general definition, conditionals are if-then statements. And that's what, when we talk about contrapositive, converse, inverse, and IFF statements, they're all about conditional statements. So if-then statements. If this, then this. So some examples. If a quadrilateral ABCD is a square, then quadrilateral ABCD is a rectangle. So it's all about using a definition. If f of x is a polynomial function, then f of x is a continuous function. Continuous is a big concept in calculus. We'll talk about that. So, okay, contrapositives, that's our first one, are the same if-then statements turned around and negative. So if the conditional statement is true, then the contrapositive is true. If the conditional is false, then the contrapositive is false. A conditional statement and its contrapositive are different ways of saying the same thing. Okay? So, and when they say conditional statement, they're talking about the original statement. So, the given statement. So, a given statement and its contrapositive are always both true or both false. So, if we look at the examples up above. Well, example 1 is write the contrapositive of each of the previous examples. So, if we look at 1. 1 was, if a quadrilateral ABCD is a square, then quadrilateral ABCD is a rectangle. So we want to switch it and make them negative. So, if quadrilateral ABCD, where am I going to go from here? Okay, so switching it, we're going to use the rectangle, and then we have to make it negative. So, is not a rectangle, then quadrilateral ABCD is what? Not a square. Easy enough? Okay, let's practice with the other one. If f of x is a polynomial function, then f of x is a continuous function. So, if f of x is what? Not a what? Okay. Is not, so we're making it negative, and we're switching it. A continuous function. Then f of x is what? Not a polynomial function. Okay, got the idea of contrapositive here? Example 2. The following conditional statement is true. If function f is differentiable at point P, then function f is continuous at point P. Again, continuous, differentiable, they're throwing calculus things in at you. But you don't have to know anything about those right now. They're just saying that if the statement is true. Make an equivalent statement that is true. So what is an equivalent statement that is true? What? So basically they're asking us to write the what? They want the contrapositive, right? So basically flip the pieces again and make them both negative. So if that's the case, then we're going to say if function f is not continuous, at point P, then function f is what? Yeah. Not differentiable at point P. Okay, so that when they didn't say write the contrapositive, they said write an equivalent statement. But contrapositive is always equivalent to the original statement, so that's why they had us do that. One last more contrapositive practice. State the contrapositive of the following conditional. If x is a rational number, then x is an irrational number. So what's our contrapositive? If x is not an irrational number, then what? X is not a rational number. Now, was this statement true? This is saying if x is rational, then x is irrational. What do you guys know? Yeah. If x is rational, then x is not irrational. Or if x is irrational, then x is not rational. Whichever way I was saying that. Okay? So that's an example where the original was false. And if you look at this one, if x is not an irrational, then x is not rational. Well, that's false also. Because basically a number is one or the other, assuming it's a real number. Okay, so converse. When it comes test time, you'll just be able to have to, given a statement, write the converse of it. So it's just memorizing, okay, how do you write the converse? What the relationship is there. Okay. Converses and inverses. Converses are conditional statements reversed. So it's like doing a contrapositive where you flip the two pieces, but you just reverse them. That's it. You don't put the negatives in. The inverse is the conditional statement just negative. So no switching, but making both pieces negative. So converse and inverse combine to make a contrapositive, but individual, they're two separate things. So converses, you reverse the conditional. Inverses, you make both pieces negative. Now, notice what it says here. The converse and inverse of a conditional statement are equivalent, as in they're equivalent to each other. The converse of a true conditional statement, though, is not always true. Okay? So converse and inverse are equivalent. Converse, whoops, that's not what I meant to do, is not always true. Okay, and I think we have to write some converses and inverses on the back side, don't we? So, example 4, write the converse. If quadrilateral ABCD is a square, then quadrilateral ABCD is a rectangle. So what's the converse say? Okay. He just flipped the pieces. Quadrilateral ABCD is a rectangle. Then quadrilateral ABCD is a square. Okay. Now, was the original statement true? Was the conditional statement true? If it's a square, then by definition, a square is a type of rectangle. Yes? Okay. Is our converse true? If it's a rectangle, then it's automatically a square? No, a rectangle can be a square, but it's not necessarily a square. So this is an example where the conditional was true, but the converse is not. Okay? Okay, example 5. Write the inverse as the same statement from 3-4. So go back to the original. If quadrilateral ABCD is a square, then quadrilateral ABCD is a rectangle. This time, inverse. How's the inverse go? Okay. Quadrilateral ABCD is not a square, and quadrilateral ABCD is not a rectangle. Okay. Got the idea there? It's not a difficult concept. It really isn't. It's a memorization thing. Okay. Are you familiar with IFF statements? Do you know what IFF stands for? IFF stands for if and only if. Okay. Okay. I had a feeling you might have. So, if and only if statements are used to combine together a conditional and its converse when both are true. So, first of all, let me write it up there. If and only if is what we're talking about. And we use our if and only ifs if the conditional and the converse are both true. So, for example, in triangle ABC, the conditional is if the measure of angle A equals the measure of angle B, then BC equals AC. The converse is the measure, or if BC equals AC, then the measure of angle A equals the measure of angle B. Okay. Based on the fact that those are both true, they can be reduced to an if and only if statement, IFF, where the measure of angle A equals the measure of angle B, if and only if BC equals AC. So it's just a way of shortening. So example 6 asks us to write our own. Use an IFF statement or if and only if statement to express both conditional statements in one sentence. If a triangle is equilateral, then it is equiangular. If a triangle is equiangular, then it is equilateral. So, how do I put this as an if and only if statement?
So a triangle is equilateral. Yeah, triangle is equilateral if and only if it's equilateral.
You got it. A triangle is equilateral. And I'm just going to use that IFF. That stands for if and only if. It is equiangular. And hopefully you guys remember, if a triangle is equilateral, all three sides are the same. If all three sides are the same, we know all three angles have to be the same, right? So it's going to work both ways. If one's true, then the other's true. Questions? Because that's today's lesson, folks.
This is much preferred.
And I'll be honest, there'll be days that happen like this when it's a quick, short lesson like this, not as difficult. There'll be days like the first day where we're pushing to get everything in and I'm scrambling. It just depends.
Can I go grab my